Hello, and welcome to this video on forces and resultant force. This is for GCSE Physics and Combined Physics, and don't forget to like and subscribe. Power, distance, mass, speed, these are all examples of scalars. A scalar is a quantity that only has magnitude, whereas acceleration, displacement, velocity, force, and momentum are all quantities that are vectors. These have magnitude and direction. Magnitude is an amount of something and it's represented by a value, a number. For example, water boils at 100 degrees Celsius. The direction for the vector can be given in the following ways. It could be an arrow, it could be written down as left, right, up, down, or north, south, east, west, or it can be given as an angle. Speed is a scalar that can be measured in meters per second, whereas velocity is a vector that is measured in meters per second. The difference is that velocity has to be in a straight line. The moment you change direction, then the velocity has changed. A car only has constant velocity when it's going in a straight line at the same speed. A force is a push or a pull that acts on an object because of an interaction with another object. It's also a vector quantity. It has magnitude and direction. All forces are either contact forces, objects are physically touching, or non-contact forces, objects are physically separated. Examples of non-contact forces are friction, two surfaces rubbing past each other causes friction, air resistance, because air particles are in contact with another object, tension, two forces acting to stretch or compress, and the normal contact force, the reaction force when a force is applied to another object. Examples of non-contact forces include gravitational force, an attractive force between two objects. It causes mass to have weight. Electrostatic force, which is a force between charged particles. And the magnetic force. This attracts magnetic materials and can attract or repel other magnets. Forces can act between objects. Newton's third law states that if body A exerts a force on body B, then body B will exert an equal and opposite force on body A. So in these examples, body A, the Earth, exerts a force of attraction on the Moon. Body B, the Moon, exerts an equal and opposite force of attraction on the Earth. And here, body A, a person exerts a pushing force on the wall. Body B, the wall, exerts an equal and opposite pushing force on the person. This is the normal reaction force. As force is a vector and has magnitude and direction, we can use arrows to represent the forces acting on an object. When drawn to a scale, the length of the arrow represents the magnitude of the force, and the direction of the arrow represents the direction of the force. Here we have a scale, one box equals 0.5 newtons. So this arrow represents 5 newtons east, and this arrow represents 2.5 newtons north. When forces act on an object, they can be balanced or unbalanced, and this has different results. In each example, the car is moving to the right, and the arrow represents the magnitude and the direction of the force. Here, the thrust is larger than the drag force. This means the forces are unbalanced. The larger thrust force will cause the car to accelerate forwards. Here, the thrust is much smaller than the drag force. Again, the forces are unbalanced. The larger drag force will cause the car to decelerate. Here, the forces of thrust and drag are the same size. They are balanced. These balanced forces can neither cause an acceleration nor a deceleration. This means the car must be travelling at a constant velocity. But what if the car is stationary? There would be no thrust from the motor, and so there would be no drag forces either. But there are still forces acting on the car. In the previous examples, the forces acting in the vertical plane were left out. These forces of weight and reaction force are balanced, so the car will not accelerate up or down. If forces are balanced, an object is either moving at a constant velocity or is stationary. A resultant force is the single force that can replace all of the other forces acting on an object and have the same effect. If the forces are in the same plane, so horizontal or vertical, they can be either added if they're in the same direction or subtracted if they're in opposite directions to find the resultant force. And you don't have to be a particularly good artist to do these diagrams either, as the object, whatever it is, a drone, a car or a plane, is represented by a circle. In these examples, we have used a scale. In the first example, we've got 1 square to 1 Newton. So our arrow going upwards is 3 squares long, which means it's 3 newtons. Our arrow going downwards again is 3 squares long, which is 3 newtons. As our arrows are going in opposite directions, we need to subtract them. So 3 minus 3 gives us 0 newtons. This is our resultant force, and it shows that the object is stationary or moving in the vertical plane at a constant velocity. In this next example, our square is 1 square is 5 newtons. So our arrow towards the left is 3 squares long, which makes it 15 newtons, and our arrow towards the right is 6 squares long, which makes it 30 newtons. They're in opposite directions, so we subtract. So 30 minus 15 gives us 15 newtons to the east or right. This shows the object is accelerating to the east. Now our last example, the scale is 1 square equals 2 newtons. We have an arrow going towards the left that is 3 squares long, which gives us 6 newtons, and another arrow going towards the left, which is 5 squares long, which gives us 10 newtons. And then towards the right, we have an arrow which is 6 squares long, which is 12 newtons. The arrows that are going in the same direction, we need to add those to get that force. So the overall force going towards the left is 10 plus 6, which is 16 newtons. Then we subtract the forces going in opposite directions, so 16 minus 12, that gives us 4 newtons either to the left or west. A free body diagram shows all of the forces acting on an object. And you've seen these diagrams in previous slides. These are free body diagrams showing the forces acting on these cars in different situations. In an exam, you may be asked to complete a free body diagram. These are some examples. A stationary cup on a table. As you are told it's stationary, then the forces on it must be balanced. You have the weight acting downwards and the normal contact force acting upwards. A ball falling at a constant velocity. As the velocity is constant, the forces must be balanced. We have the weight acting downwards due to gravity, and this time the upwards force is air resistance as the ball falls through the air. The resultant force of two forces at right angles can be found using a scale diagram. In this question, the object has a 40 Newton force acting north and a 30 Newton force acting towards the east. You need to find the resultant force. First, choose a scale. 1 square equals 5 newtons, for example. Draw in the forces. Make a rectangle using your force arrows as 2 of the sides. Draw an arrow from the object to the far corner. Use a ruler to measure this arrow and apply your scale. Use a protractor to measure the angle to the vertical. So in this example, drawing it to scale and measuring with our ruler, we have our 50 Newton force, and using our protractor to get our angle, we have a 37-degree angle from the vertical. The reverse process can be done. It's called resolving forces. Draw a rectangle around the force arrow that you have been given. Add arrows to the vertical and horizontal sides. Measure these arrows with a ruler and apply any scale. These are your vertical and horizontal components of the force. And that's all for this video. Thank you so much for listening.